Alrighty, so we are almost done with chapter 6, I would say. We're about maybe halfway through. We'll definitely finish it today. So remember your exam that is on Wednesday will cover chapters 5b, that was Lewis structures, as well as the shape and polarity idea. It will cover chapter 7, which was gases. And then it will also cover this chapter, chapter 6, which is on intermolecular forces. So last time, remember we talked about 3 different types of intermolecular forces, right? We talked about hydrogen bonding, which was a nice strong force. We had dipoles that involved hydrogen. Yeah, Robert, it's essentially that equation. That's pretty much the majority of chapter 7. So, let's see. We remember hydrogen bonding is very strong because hydrogens are very small, and typically we get dipoles with them, especially if it's on a very electronegative element. And so as a result, molecules can get really close together, and the closer they are together, the stronger those forces are going to be. We also had just plain old dipole-dipole interactions where polar molecules, which have a positive end and a negative end, can associate with the positive and negative of another molecule. Obviously, we would want the positive from one and the negative from one to come together. Oh dear. Oh, like this camera? Okay, I see what you're saying. I think it's because it's in the back, so let me turn that off for a sec. Ta-da! Okay, is that better? Like, did you mean like the camera of me? Or like... Okay, cool. Yeah, sorry, I guess the tab had gotten behind. Cool. And then the last type of force we talked about was the London dispersion force, where electrons are just kind of randomly sloshing around a molecule or atom, and at one point they could tend to be on one side of that atom or molecule. And as a result, we have a very small positive and negative on that molecule or atom, which can then attract other atoms to do the same thing. As a result, we create an instantaneous temporary dipole in another molecule, and those can have a minor attractive force. We also saw anything can do London dispersion forces, and typically the more electrons you have, that is your higher molar mass, the stronger that force will be, just because you'll have more electrons to move around. So, did we have any questions on those guys? Or on gases, I guess. We can talk about that too if any of you have questions. Don't forget you do have homework due tomorrow on that. Yes, polar molecules only. Yeah, Rob, it'll be the same thing as last time, so you'll just go on Canvas at 3:30 and take your exam right on Canvas. Yeah, homework will be due tomorrow at midnight. Or rather, 11:59, yeah. Alright, let's see what Samuel's got to say. Yep, same thing. So open universe, multiple choice through Canvas. What are you sad about this time? Oh, I know, Zoe. I was actually doing the same thing, and I was like checking Discord at like 2:30, and I was like, please, nobody be on for office hours. I want to sleep. So, oh, well, that's nice. Okay, you can deal with lab on your own. Cool. Okay, so with no questions, we're going to go ahead and talk about the the effect of these intermolecular forces. So, like, what's the point? Does anybody have any idea, out of curiosity? Maybe you've read ahead in the textbook, but there are ramifications to these intermolecular forces. The most obvious one for us is melting points and boiling points. We remember melting, hopefully you know, is solid which does not start with SL, but in fact SOLID. Very good. And boiling was liquid to gas, right? Well, sorry, I can't control how fun the lab is. Yeah, slolided. Yeah. Okay, so melting and boiling points are directly related to your intermolecular forces. So we're going to see that the stronger your forces are going to be, the higher these points will be. The reason is you need to put in energy to break these bonds. Anytime you are breaking a bond in chemistry, you have to put in energy to do it. Okay, so to break intermolecular forces, you need to put in energy. All right, just out of curiosity, if we're putting in energy, is that endo or exothermic? Let's go back to whenever we talked about that. Quick vocab test on that. Yeah, that's endothermic, right? So anytime we're breaking bonds in chemistry, that's endothermic. Okay? Endo. Takes energy to do it. Yes, exo is releasing. So endo, we're putting in energy. All right, so if you imagine in a nice, let's see, we've got water maybe. We know water tends to form nice hydrogen bonds, right? All these waters can kind of get nice and close to each other, and they're all happily kind of interacting, right? We can see that these are pretty strong attractions because water, even though it's a tiny molecule, it's 1 oxygen, 2 hydrogen, that's it, has a very, very high boiling point, relatively speaking. We know there are a lot of gases that are bigger than water. For example, butane or propane, those are hydrocarbons. Those are, 4 or 3 carbons with a lot of hydrogens on them. A lot bigger than this water molecule is. But those are gases at room temperature, while water is a liquid. The reason water is a liquid is because these bonds are so strong. So we know that the temperature is related to how much kinetic energy something has, right? It's how fast things are moving. And so you can think, in a liquid, these molecules are all just kind of sloshing around, but they're all kind of following each other, right? Because they're going to be wanting to follow those nice positive and negative interactions. And so all these other molecules are just going to do the same thing. They're just going to follow along in this, random flowy pattern. If we want to make this liquid into a gas, we have to break all these bonds. We have to release, let me use another color for that. We have to release, let's say this one. We have to get that away from the other ones. And in order to do that, we need to make it move faster. The faster that one is moving, the more likely it is to kind of just break off. So if you imagine they're all in this conga line, right? They're all just like flowing around each other. And one of them just gets super excited, lots of energy, lots of kinetic energy. It eventually will just kind of, it can't, since it wants to move so much, it can't really stay in that position and it'll kind of break off. And so the more energy we can give this, the more of these molecules are going to kind of move like crazy and they're going to break off. So we're going to be able to kind of liberate these molecules from their intermolecular forces by putting in heat or putting in energy. Which is why anytime we want to boil something, if you put a pot of water on a stove, you have to turn that stove on, right, to get it to go into the gas phase. So we're going to see that it's because of these intermolecular forces that water prefers to be a liquid, but you can make it go into a gas by giving it more energy. That is to say, at room temperature, at least. Okay, does that kind of make sense? Anybody have any questions on that kind of idea? Main point there, put in energy to break intermolecular forces, and if you do that, you can change the state of matter of your substance. And we also saw that the stronger your forces were, the higher your melting and boiling points were. So freezing would be releasing energy, yeah. And same thing, if we were to condense a gas, we are releasing energy. You want to know how your fridges work? Let's talk about that. That could be cool. Okay, refrigerator. Box here, yes? There it is. In the back of your refrigerator, you've probably seen, there's often like this kind of crazy radiator thing, right? Coils. And you have this kind of blob at the bottom called a compressor. You don't have to know the names of this stuff, by the way. This is just kind of illustrating a point. In this, we have a liquid with a low boiling point. All right, so the liquid is kind of interfaced with your refrigerator. Could be Freon, there could be pentane, there could be a bunch of other random ones. Freons are typically not used anymore just for environmental reasons, but some liquid that boils at a low temperature in there somewhere. And as your food in your refrigerator, let's say we have, what do we have in our fridge? Well, very clearly we have bottles of wine, right? There it is. Okay, there's our bottle of wine, okay? Oh god, oat milk. And so, maybe you know this, but things constantly kind of give off heat, right? And so this thing is kind of giving off heat as it goes. And eventually that heat kind of goes to the back of your fridge, still on the inside. And in that kind of interface at the back of your fridge is where this low boiling point liquid is. And that heat will be absorbed by that liquid. And then that liquid will boil. It will turn into a gas and travel up these radiator coils, and eventually it will condense again. Remember, a condensation is when a gas goes back to a liquid. And when it does that, condensation is exothermic, right? It's going to be giving off the energy in the back of your fridge behind it in those radiator coils. And you'll see that if you go to the back of your fridge and you put your hand there, it's going to be warm because that liquid is giving off its energy outside of your fridge in the back. Or some fridges it's on the bottom facing out. And as a result, the inside of your fridge is going to get cold because the substances in there give off their heat, and the fridge absorbs that heat. So the more that the fridge can absorb heat, the more heat can be given off by the stuff inside, therefore getting it colder. And then that boils a liquid, which then goes up through these radiator coils, releases that heat, and transforms back into a liquid, and then condenses back down again. So that's kind of how fridges work. So our freezers too, it's the same idea. So just depending on what liquid you have, that kind of controls the setting. You also have a compressor in there to also kind of manipulate the pressure, which will mess with the boiling point a little bit. So, cool. Okay, that's an example of the point of all this stuff. Cool. Alrighty. How many of you have ever done that thing where you take a penny, beautiful drawn penny, and you drop water onto it? You notice that, the more water you put on it, you can actually put quite a bit of water on this thing before it starts falling off. You can try this at home. Not dangerous. Exactly, we're going to talk about surface tension now. So, this water, instead of just spilling out over, will actually kind of form this dome shape on top of that penny. And you're going to be able to kind of really create, or really put a lot of water on that before it falls off. Same thing, yeah, physics, hooray. You can also see, you can overfill a bottle or a cup or something, and you're going to again see that kind of dome shape without the water spilling out everywhere. The reason for that is, you have a water molecule There it is. And let's say we have a bunch of other water molecules that will be darker blue. And that water molecule is kind of attracted to all of those, right? Its positive side and its negative side are attracted to the positive and negative of other waters, right? And so all these waters are kind of pulling on that middle water at the same rate. So they just kind of sit there. However, at the top of your liquid, there's our water molecule again. We only have molecules that are kind of below it. We don't have any on top because we're at the surface. And so we can see that overall, this light blue water molecule is kind of being held down. All those molecules below it are kind of holding onto it with those intermolecular forces, those hydrogen bonds. And as a result, that water molecule can't really escape very easily, which relates to thus having this kind of dome shape. Another implication of this is you might have seen water bugs if you ever go hiking or anything like that. You can see these bugs walking across the water, right? They're small enough and they're able to kind of spread out their weight that they can take advantage of this. They can push down on these water molecules that can't move out of the way because these other water molecules are holding them there. And so these bugs can skeet across the water. You can also float a paperclip on water. That's another pretty cool thing. If you just take some tweezers and put the paperclip into a bowl of water, it'll float there, even though it's more dense than the water. The reason, again, is because that water does not want to break what's called this surface tension. Let's see, what color shall we use? Black. Oh no. Surface tension, yes. All right, let's see what Tiffany has to say. Well, while she's telling that, I'll tell you another cool thing you can do at home. Oh my god, you beat me to it. Okay, so surfactants, yes. These are a class of chemicals that mess with surface tension. So they prevent surface tension from forming. So if you want to see this in motion, take some pepper, just black pepper, grate it on top of a bowl of water. And you're going to see the pepper's just going to float on the top. Same idea here, the surface tension will keep it there. And if you put a drop of soap into that water, you're going to see all that pepper is just going to like whoosh, get out of the way. It's going to move to the sides. It's pretty cool. If you also try this with that paper clip, if you put soap into that water, you're going to see it will cause the paper clip to sink. Because soap molecules actually mess with the surface tension of water. They're called surfactants. They mess with these things. They interfere with these intermolecular forces. So that's another way we can do it. We could add heat, or we could add other chemicals to kind of mess things up. So that's something you can try out. So try it out. Pepper on water and then put some soap in. You'll watch the pepper just like whoosh, get out of the way. It's pretty cool. Again, not something that will be tested. So, but that's the idea. So surface tension is one reason that we have this. Okay. Cool. So we also have viscosity as another implication of these intermolecular forces. And that is kind of how flowy something is. Okay, it's essentially its resistance to flow, but that's okay. You've seen, perhaps, water moving. You can flow water fairly easily, right? You can take water and pour it from one container to another container. We can also do the same thing with honey, right? You can take honey and pour it into another container. However, you've noticed that honey will take a lot longer to move from that top container into wherever you're pouring it. The reason is because honey really likes itself. It's really got these strong intermolecular forces that kind of keep it where it is, that resist that kind of gravity of trying to make it flow. So honey is going to be very viscous, Whereas something that's a gas, for example, is not viscous. Gases are super easy to move around. You can just... I've just moved all this gas out of the way just by blowing slightly. And so just kind of the opposite. And then we just have, kind of water in the middle. I mean, water's not really that viscous either. We can pour it really easily, right? It just like pretty much instantly. But technically there is a little bit of resistance there. Gases would just completely... I don't know how you can do it faster, but pretend it's faster, I guess. Okay, so that's another thing. So this means that honey has strong IMFs, and gases have weak IMFs. Okay, IMFs are intermolecular forces, right? So the stronger your IMFs are, the more surface tension you have, the more viscosity you have. So that means you are able to form these nice kind of domes or circles you can bead up, really is what it is, nice and easily, and you also don't move very nicely. Okay? Do you have a question, perhaps? Yeah, gases have 0 IMFs, technically. We make that assumption, but technically they can do London dispersion forces, right? But they're very, very, instantaneous. So just, one gas molecule here and here, maybe they're just kind of moving towards each other a little bit. And so there is that relationship, Sarkis. But technically we usually assume that gases don't have intermolecular forces. Let's see. Yeah, it's definitely related, right? Because the more dense something is, we can also think about the more electrons are within an amount of space, right? The more dense something is, the more kind of the atoms are really tightly packed together, right? And so there's definitely that relationship there. The more close they are together, the less likely they are to, tumble around it and move from container to container. But however, there's it's kind of just a rule of thumb. You can think of vegetable oil as actually more viscous than water is, but it is less dense. So there are certainly exceptions to this, but typically that is a fair trend. Okay? You could try it. Try pouring out some oil. You'll see it moves a little bit more slowly than water would. Cool, but it floats on the water. Alrighty. Any other questions on that? Okay, just some implications. So, really what we've got to summarize here is the stronger your IMFs... Goodness gracious, I'm really just pulling Manuels all over the place today. Oof. The stronger your surface tension will be. Oh my gosh. Wow. Surface tension. There we go. Stronger surface... Yes, you did. Stronger surface tension. Stronger viscosity. And we also have... You know what? Let's forget stronger. Let's say higher. Boiling point and melting point. Also, it's didn't. Oh, I see. Catastrophe. Okay, so those are kind of the implications. So the stronger your IMFs are, you're going to have higher surface tension, higher viscosity, and higher boiling point and higher melting point. Okay? Thankfully, all of these are, it's a pretty nice direct relationship. The stronger your IMFs, the stronger these things are. So there's none of this. We don't have to worry about one goes up, one goes down. They're all kind of proportional to each other. Alrighty, so hopefully that's not too crazy. Any questions on that? Cool. I told you this chapter is not going to be too much craziness. So in fact, we probably will finish by 4:30 today with this chapter. for which point we can just go ahead and end, and I'll stay around for the other hour for you guys to have ask questions, anything about the stuff for the exam, okay? Yeah, of course, you know, when we end, if you don't want to hang around, that's perfectly fine. Yeah. Okay? Cool. So, let's talk a little bit about... Hi, Kaz. Let's talk about... Yeah, we probably won't take a break. Or we could, and then we could just come back after. So, if you want. Okay, we know solids can go to liquids, right? What's that called? Yeah, so we can probably just take a break, and then people who don't want to come back don't have to come back. Yeah, that's melting, right? And if we go the other way, that's called freezing, right? Okay, let's see. We can also go from liquid to gas, right? That is called evaporation or boiling. Same thing, right? We can go backwards, and that's called condensation. We can also go directly from solid to gas. That's what dry ice does, which is something called sublimation. In the textbook, we made a pretty cool video of iodine subliming. So iodine is a normal solid. It's kind of silvery metallic, but it actually produces a purple gas when you heat it up. And so it goes directly from solid to gas, subliming. So you can see it. We've done pretty cool things. So you can watch this iodine turning into this purple gas. And then later we do the opposite. We call deposition. We make that gas deposit back into a solid, and you can see these pretty iodine crystals forming on the lid of our container. Cool. So these are all the processes. Probably this is not new information for any of you. You typically have heard of these terms before in your everyday lives. But we should know that in this class, did we talk about endo and exothermic being positive or negative? Have we talked about that yet? No. Okay. So typically chemists will indicate something endothermic with a positive change in energy, because energy is being added, it gets bigger, right? And exothermic is a negative. So, between melting and freezing, which one of those is going to be exothermic? Which one gives off energy? Yes, you're absolutely right. So freezing gives off energy. So you're going to put something warm into the freezer. You would come back later. It is colder, and it is now a solid. It has given off energy. Conversely, melting will be endothermic, right? You have to heat something up to get it to melt. If you wanted to melt some candles or some wax, you would put heat on it, right? And you would melt that wax. Okay? Just like before, evaporation and boiling, we have to put in heat to get that to happen. We have to heat up our stove, turn on the stove to get that water to boil. Therefore, condensation will be our exothermic equivalent. And now, let's take a guess about sublimation and deposition. Which one of these do we think is going to be endothermic? Would that be solid to gas or gas to solid? So we have a half and half response here. Let's think about the intermolecular forces for a second. We know gases pretty much have none. Tire breaker, Rob? Now you're channeling Manuel as well. Gases have basically no intermolecular forces, right? They're all broken. Whereas solids have pretty good intermolecular forces. So if we're putting in energy, are we going to be breaking forces or making forces? Yeah, we put in energy, we break those forces apart. So as a result, the endothermic one will be sublimation. That is going from intermolecular forces, that's solid, breaking those into a gas. Okay, and then deposition, therefore, will be our exothermic one. Okay? We can also think of it kind of like the more orderly you're getting, the more energy you have to give up. I don't know if that helps. Or the more crazy you're getting, the more energy you have, right? So solid is kind of nice and rigid, and you give it energy, it becomes flowy and whooshy, and then you give it even more energy, it just goes crazy and has gone all over the place. Okay? Cool. Typically, we talk about the energy needed to do these with a, let's see, how can I describe this? The amount of energy we typically describe as delta H, of course, because that makes sense, right? This is technically the change in enthalpy. Crazy big words, right? Which is, in real language, that's the amount of heat needed to change state. Okay, and delta H comes in a few flavors. Let me actually just pull up some numbers so I don't have to lie to you guys about all these. Okay. We have delta H for freezing of water. Delta H is going to be different for every substance, okay, and every state of matter as well. We also have delta H for melting water. Right, we're going from solid to liquid versus liquid to solid. So freezing, we've already said, is exothermic, and it turns out that this value is going to be negative 6.01 kilojoules per mole. And the value of delta H for melting water is positive 6.01 kilojoules per mole. So the energy needed to freeze something and the energy needed to melt something are identical in terms of magnitude, how much energy. The only thing that matters is, are you putting energy in or are you taking it out? The same amount of energy is going to be required to do either process, right? But it's positive when you melt it. You're putting in energy. The energy is getting bigger, positive, and you're taking away energy to freeze it, right? You are lowering the amount of energy that it has, and that's why that's negative. Okay, so the idea here is all of these processes that we see, freezing and melting, evaporation and condensation, sublimation and deposition, those have the same energy as each other. Okay, but the only difference is which way that energy is going. Okay? Typically, the energy from solid to liquid is a lot less than the energy from liquid to gas. Does anybody have any idea why? For example, for water, it's 6.01 kilojoules per mole, and then 44 kilojoules per mole. I like your ideas, yeah, definitely related to those hydrogen bonds. Not necessarily, Sample. Since these are both per mole quantities, they both relate to the same number of. Yeah, Tiffany, I think you're getting it. Yeah, definitely. What about the movement? Faster, yes. Solid is slower, yes, that's true. Farther apart. That's kind of more what I'm going for. That's what I like to hear. We know that solids and liquids both have molecules that are pretty close together, right? Exactly. So that's a very nice description, Marissa. So these two both have molecules close together. Both of these guys. And this one is far apart. So breaking a solid into a liquid, we're not really trashing all those hydrogen bonds. We're just making them, kind of less orderly. They're now flowing around each other. But going from liquid to gas, we have to completely break apart those hydrogen bonds. We have to completely release all of these molecules from all their interactions with others. Yes, I think that emoji works just fine. Very good. Okay, so that's why typically liquid to gas takes a lot more energy than solid to liquid does. Shall we see this in a problem? We love math, right? Yes. Okay, so how much energy in kilojoules is needed to melt 500 grams of ice? And then to boil Okay, we can go ahead and say that I'm going to give you two constants here. I'm going to give you delta H fusion. Fusion, by the way, is what we call melting and freezing. And that is 6.01 kilojoules per mole. Okay, I'm also going to give you delta H vaporization, which, guess what, is the boiling and condensing delta H. And that one we're going to say plus or minus 44 kilojoules per mole. Alrighty, so guess what? These delta H's are conversion factors, right? We have some unit divided by another unit, right? That's a conversion factor. So if we want to find kilojoules of something, and we're given a conversion factor of kilojoules per mole, what other information are we going to need? If we want kilojoules and we have these conversion factors, what do we need to find first? I mean, yes, you're correct. We need to find the moles of water, right? By doing that, we're going to use the molar mass. So, let's go ahead. Let's do the ice one first. Is the ice one going to be relating to this melting or freezing, or boiling and condensing? Is that delta H fusion or delta H vaporization? It's fusion, right? So let me actually write that out. So that's fusion, right? And that's, oh no, vaporization. Okay, so yeah, we're going to use delta H fusion here. So we have 500 grams. with our molar mass, which one is going to be on top and which one on bottom? Like which units? Grams on bottom, yes. And then all we have to do is use our delta H fusion. So we know 1 mole is going to go on the bottom. Alrighty, and so we are melting this ice. So are we going to use the positive or the negative delta H? Okay, again, okay, looks like 3 out of 5 have it correct. 4 out of 6, actually. Yeah, so it's the positive one, right? Because if you want something to melt, you have to heat it up. That's the molar mass of water. Sorry, Arpin. That's just one that I definitely have memorized. So that's 2 times 1.008 plus 16. That's the molar mass. Sorry, I guess I did not make that super clear. Okay, since this is water, right? It's ice. Ice is H2O. Cool. I'm sorry, I forgot our unit there. This is kilojoules, right? So remember, you just always think about it. If you're melting, you have to give it heat. Okay, so if you wanted to melt that ice, we're going to have to give it energy that's going to be positive. Alrighty. Someone go ahead and calculate faster than I can. Let's see if I beat you. I win. Oh no, kilojoules. Is this correct? Oh my goodness. I hate when I'm near the side of it. Okay, 166.759 kilojoules. Aha, yes indeed. We need our sig figs. How many sig figs shall we use here? I agree, 3. So that should be 167 kilojoules. Actually, this delta H, we're going to have to use the sig figs for that, yeah. So, because that is a measured quantity. Okay, is that all right? So that is our answer for the first one. We're able to see that it takes 167 kilojoules of energy to melt that ice. Alrighty. Moving on to the second one, we have the same mass of water, but this time we're going to be boiling it. So, oh my gosh, that's so ugly. It's a music note. Wow. I guess I'm done with the semester, everyone. 1 mole over 18.02 grams. Same thing as before, it's the same substance, the same water. But this time our delta H vaporization is 44. And is this one going to be positive or negative? We're boiling it. I know it was. Who's going to break the tie? Okay, I would agree. This is also positive. So remember back our happy triangle of things. Evaporation and boiling is going to be positive. Okay, we have to put in energy. We have to give it energy. Okay, so this one should be positive as well. Okay, doing this, we get 1,220.86 or something kilojoules. Sig figs, now we have how many sig figs? 2, yes, very good. So that is going to be 1200 kilojoules. And so, to melt that ice takes about 167 kilojoules, but to boil that, to turn it into a gas, it takes, what is that, it's almost 10 times as much, right? It's maybe like 8 times or something. It takes quite a bit more energy to go from liquid to gas than it does from solid to liquid. Okay? Remember that because solids and liquids are closer together in terms of molecular structure, those will be more similar, and so it's easier to make that transition. Okay, fun fact. Did you know that while you are boiling water, its temperature does not change? If you don't trust me, which you never do, go stick a pot of water on the stove, let it boil, take the temperature as soon as it starts boiling, come back in 10 minutes, take its temperature again. Come back in an hour, take its temperature again. You're going to see that it should be about the same temperature. Because while we're changing these states of matter, we don't actually change our temperature. You remember that if we had a solid, liquid, or gas, and we were just giving it energy, do you remember we used our MCAT formula for that, right? We use the mass, the specific heat, as well as the temperature change. Because we could heat up water. We could make it go from one temperature to another temperature. However, when you're changing the state, when you're going from solid to liquid, or liquid to gas, the temperature does not change. And so we do not have a delta T element in these calculations. Same thing, ice water will always be 0 degrees. You can just have, 1 drop of water and a whole bunch of ice. You're going to see that that water will be 0 degrees Celsius. And you can have, all this water in 1 cube of ice, provided it's completely, mixed, it will also be 0 degrees. So anytime you're changing states, you have both states present, you're going to have the same temperature. Okay? Cool. Again, fun facts. So, one more thing about this liquid to gas transition is, I don't want to explain the physics of it too much. You can read about it in the textbook. But we're going to see that in order to make something boil, we know that because we've already studied gases, here is our lovely liquid, molecules are always just kind of coming out of that liquid, right? Well, I guess I can't say right. They are. Occasionally, molecules will have enough energy, they'll just jump out of the liquid, and they'll become a gas. You know that if you just leave a bowl of water out over a couple of days, it will evaporate over time, right? It doesn't boil necessarily, but it will eventually leave, just because water molecules can escape, a few of them at a time. We also know that the atmosphere is always pushing down on our liquid, right? Just gases that are floating around out there are always kind of just bonking into that liquid surface. And so, at normal, situations, that water molecule that escapes, that it's now up here, will be smacked by those gases, and it will go back into the water. All right, the oppression, right? The gases in the atmosphere are pushing down on the water, always. Just gases are randomly moving around, right? They bonk into that water, they can send it back into the liquid state. So, that normally happens, which is why water does not randomly boil at room temperature. Because we have atmospheric pressure pushing down, pushing those water molecules back into place. A couple, of course, do escape. It's not every single molecule that this happens with. However, when something is boiling, so this is kind of normal. the last one. At boiling, we now have, a lot of molecules that are coming out. And we have that kind of same number of gas molecules in the atmosphere as before. But we can see now that with a lot of water molecules kind of pushing back at the gases, a lot more of them are going to escape. And so, if you remember from chapter 7, we have that thing called the partial pressure, right? It's the same idea. The stronger our vapor pressure is, that's the pressure of liquefied gas. No, I'm sorry, gasified liquid. Of liquid that just turned into gas. When that vapor pressure gets high enough, that means the more molecules that are there, remember that pressure is related to how many molecules you have? The more molecules you have that are coming out of that water, the greater that pressure will be, right? More molecules, more pressure. When that pressure equals atmospheric pressure, that's what's called the boiling point. So the temperature at which your vapor pressure is equal to your atmospheric pressure is defined as the boiling point. And so, you may have read at some point in your life on like a package of pasta or something, or rice, where it says, boil for whatever amount of time. And some of them will actually say, there's an elevation correction. So consider at sea level, here we are with our boiling water, versus on the mountaintop with our boiling water. Okay, you know what? Let's make this, forget this picture. We draw a bigger picture. Here's the globe. Okay, and now we have this mountain. Okay, and here's where we are. If we consider we have the atmosphere above, right? The atmosphere above the planet. The atmospheric pressure is going to be all of this stuff at sea level. But if you're at the top of your mountain, you have less atmosphere pushing down on you, right? You're a lot of the atmosphere is actually below you, and that's not pushing you down. That's just kind of not even in the way. So as a result, if you're up on this mountain, there's lower atmospheric pressure, so your water will boil at a lower temperature. So at elevation, things boil at low temperature. All right, it may not be the biggest change. It may be like 90 degrees instead of 100. But that's enough to make it, add an extra minute to your cooking time. Just because low atmospheric pressure means that you have an easier threshold to overcome. You can have fewer gas molecules that are coming out of your liquid, enough to overcome that atmospheric pressure. Okay? I think I actually saw that. So one of my favorite Armenian products is the Near East rice pilaf. I love that stuff. And that was, I think, the first place that I'd actually read about this elevation thing. So you'll see on the box there, if you read the boxes, they will say, elevation correction, add another minute or whatever it is. So cool stuff. So unfortunately, they completely sold out of it. I've not been able to get my hands on any. I'm very sad. So extra credit, find me some rice pilaf, send it my way. Okay. Oh crap, that was recorded. Just kidding. Okay, cool. So, we have one more topic to talk about. I'm going to have to post it, don't worry. Okay, how could you not like rice pilaf? It's like the most delicious thing. Okay, so last thing we want to talk about. It is true. It is easy to make from scratch. This is absolutely true, and you have more control over what flavorings you have. Of course, I've had baklava. It's too sweet for me, though. I typically don't like desserts and pastries as much. Okay, solids. We'll get back to this, Rob. Solids can exist in a couple of ways. I agree, homemade is the best. I love cooking. In fact, that's like all I've been doing is watching cooking shows and all that stuff during our hiatus from school. Okay, which of these looks more organized? As an orderly. Yeah. We have a couple ways of amorphous. We have a couple ways of talking about solids. Certain solids are crystalline, meaning that they form nice orderly patterns. And some are amorphous, which are just kind of randomly distributed things. So a couple examples. Amorphous things would be like glass. Glass has silicon dioxide just kind of thrown randomly around, no particular order. Oh, good idea. I think I might make birria if I have enough stuff. I should have enough dried chiles. Oh, okay. Stop distracting me, guys. Yeah, anyways. Crystalline stuff would be like, for example, what's a good crystalline one? Ice. Ice is typically quite crystalline. And so crystalline ones you can typically see, so think of a snowflake. For example, you know, if you see those are like nicely, look, that's my beautiful snowflake. It's very patterned, right? If you look at a snowflake under those electron microscopes, you can see they're very, you know, exact patterns that are really cool. Whereas something like glass, the molecules are just kind of thrown around each other. Okay, those are two types of solids we have. Okay, solids can be either one. They can be amorphous or they can be crystalline. Just vocab right now. Okay, cool. We also have different ways of making solids, right? We can have solids that are like diamond, which are actually covalent bonds. Or we could have solids that are ionic. And you might have seen ionic solids before, where we have positive and negative. I'm just going to do like 2 rows because forget it, it's going to take forever. Where we can have alternating, you know, like positive and negative, like this. So this is why we don't necessarily talk about ionic compounds as molecules, because like this might be sodium and that could be chloride. You can never just get like one sodium and one chloride together. They in fact form these structures where you have sodium, chloride, sodium, chloride, sodium, chloride. And so they're not really discrete entities. You usually form these crystals, these network lattices. Okay, those are just called ionic solids. So this could be like NaCl, or most ionic compounds will form these ionic solids. This would be, for example, diamond. Okay, where you just have all of these carbons connected to each other. Okay. There's one more called a metallic solid. You have seen a piece of metal, presumably, in your life. How metals work, it's pretty interesting. Metals, as we know, they kind of have just like loosely, their electrons are kind of just loosely held, right? We know that metals tend to lose electrons fairly easily. And so we often describe metals as solids, as in you have a piece of aluminum or something, as a sea of electrons. 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 Where these things are electrons, and these things are, let's say, metal atoms. And so all of those atoms are just going to kind of be positively charged, just because all these electrons are just kind of floating around within them. And so electrons can just swish and swash like an ocean in between metal atoms. And so as a result, metals will also form solids because of these relatively nice interactions that they have. Okay, so we have kind of three types of solids that we have. We have covalent solids, we have metallic solids, and we have ionic solids. Any of those can be crystalline, and any of those can be amorphous. Typically, ionic solids are going to be more of the crystalline sort, but it is certainly possible to have all of these in different ways. Okay. Questions? There's a nice chart in the kind of last part of this chapter in the textbook that summarizes all of this stuff, so you can just go ahead and refer to that to see about these solids. Okay? Great. Okay, so we are done. We can take our break now. If you want to go ahead and skip town and go nap some more, you are more than welcome to do so. I will come back in about 10 minutes and I will answer questions that you guys have. Okay? Alrighty, I'm going to go ahead and save our video.